Welcome back to GISC 1336. In our first lecture, we looked at surveying as a civilizational practice, the act of measuring and recording that made agriculture, taxation, and empires possible. In our second lecture, we turned to the drafter, showing how raw measurements become meaning through careful translation and interpretation. Today, we pivot again, but this time into one of the deepest conceptual topics in surveying and civil engineering: surfaces and grading. When you hear the word surface, you probably think of something tactile, like the surface of a desk, the surface of a road, or the surface tension of a pond. But in engineering and surveying, a surface is not just what you can touch. It's a mathematical abstraction. It's a model of the Earth's surface, its skin, a representation of terrain that lets us analyze slopes, drainage, and elevation differences in ways that simple field notes never could. In other words, surfaces are how we take the messy, irregular, complicated ground beneath our feet and turn it into something that can be measured, designed upon, and reshaped intelligently. That's why today's lecture is titled Surfaces and Grading in Survey Engineering. We're going to be exploring what a surface is in theory, why different kinds of surfaces exist, and how they're used to communicate terrain, and how grading transforms those surfaces from existing conditions into proposed designs. By the end of this lecture, you should not only know the definitions of TIN, DEM, contour, and grading group, but you should also understand why these concepts matter, how they connect to both the science and practice of our field, and how they form the backbone of modern site design. Let's get to it. At its core, a surface is a three-dimensional mathematical model of terrain. It translates irregular scattered elevation measurements, what a field crew collects, into a continuous representation of the land. Why do we need that? Well, it's because the Earth itself is continuous, even if our data may not be. Think about it. When a survey crew goes into the field, they don't measure every square inch of a site. They take discrete shots. A point on the top of a hill, a point at the bottom of a ditch, maybe a few along the slope, maybe a few hundred points on a tract of land that actually contains millions of square feet. If we left those as just dots in space, we would have an incomplete picture. A surface is the tool that interpolates between those dots, creating a continuous model of elevation that approximates reality. This interpretation is not guesswork. It's grounded in mathematics and geometry. Surfaces rely on methods like triangulation or grid sampling to fill in the gaps between measured points. They turn our scattered observations into a coherent whole. That's why surfaces can be so central in engineering. Without them, you'd be trying to design a road or a subdivision or a drainage plan based on a cloud of dots. With them, you have slopes, volumes, contours, and models that you can calculate from. Our produced surfaces serve as a communication tool, the visualization of the real world to a plannable object. It makes it easy to think about surfaces as a language. Surveyors speak in points and elevations. 0.325, 512.43 feet. Engineers and planners, however, they think in slopes, drainage paths, and building paths. The surface is the translation layer between these two languages. It allows the surveyor to hand the engineer something meaningful, and the engineer to hand the contractor something buildable. Historically, this translation has always existed. Medieval surveyors sketched ridges and valleys on vellum with ink that suggested certain terrains. By the 19th century, cartographers drew hand-contoured maps with painstaking attention. Today, we use Civil 3D, which dynamically generates contours from digital surfaces. The principle is the same across time. Raw measurements must be turned into continuous pictures of the land before it can be useful. So now that we've framed surface conceptually, let's classify them. There are three main ways we represent terrain in practice. We have tin surfaces, triangular irregular networks. They're flexible, precise, and built from triangles that adapt to data spacing. Then we have DEM surfaces, or digital elevation models. These are grid-based. They're less detailed, but they're efficient and widely available. And lastly, we have contours. These are traditional lines of equal elevations, intuitive for human interpretation. Each of these is a different way of answering the same fundamental question. How do we turn discrete elevation points into a continuous model of the Earth? TINs, they emphasize precision and local accuracy. DEMs, they emphasize coverage and compatibility. And lastly, contours, they emphasize readability and tradition. As we go deeper, we'll see why engineers and surveyors choose one surface type over the other depending on the context of their projects. But before we dive into each surface type, let's make the connection to grading clear. Grading is the process of reshaping the terrain, cutting, filling, leveling, and sloping land to serve a design. Whether it's flattening a pad for a building, cutting into a hillside for a road, or shaping a basin for stormwater, grading decisions all start with the surface. You can't know how much dirt to cut unless you know what the ground currently looks like. You can't fill volumes unless you have a model of both the existing and proposed conditions. You can't predict drainage without knowing the slopes of the terrain. In short, grading is the art of modifying surfaces. The surfaces are the science of representing terrain. These two are inseparable. So, now that we've established what a surface is in general, let's begin with the most important type for surveying engineers, the triangular irregular network, or TIN. At first glance, a TIN may look like nothing more than a web of lines connecting survey points into spider webs of triangles. But there's deep geometry behind this. A TIN is a way of answering the question: if we only measured certain points on the ground, how can we best represent everything between? The answer, obviously, is triangles. But why triangles? See, triangles are the simplest polygon in geometry. Unlike squares or hexagons, a triangle is always flat. 3 points define a single plane. That makes triangles perfect for modeling terrain. Imagine you have 3 survey shots: the top of a hill, the bottom of a ditch, and a point in between. If you connect those with a triangle, you can interpolate the elevation anywhere inside that triangle by assuming the surface is flat between them. That assumption is locally reasonable because 3 points are the minimum needed to describe a unique plane in 3D space. By stitching hundreds of thousands of these triangles together, we get a continuous approximation of the terrain. Some triangles are steep, others are flat. Some large, others small. But together, they form a flexible mesh that adapts to the land's irregularities. And one key feature of a TIN is in its name: irregular. Unlike DEMs, which use evenly spaced grid cells, TINs don't force the data into a uniform grid. Instead, triangles are drawn wherever the survey points happen to lie. That means, in areas where surveyors collected lots of detail, say around a building pad or a drainage ditch, the TIN will have small, dense triangles, capturing subtle variations. In open fields with few changes in slope, the TIN may use large triangles because there's no need for excessive detail. This adaptability is what makes TINs so powerful. They respect the distribution of data, putting detail where detail exists. And I know I don't have this on the PowerPoint, but another important thing to note about tins is that the vertices of each of these triangles is an actual measurement. It's not an average or an assumption. It is an actual measurement that's collected. Another reason why these respect a lot higher grades of accuracy. So let's get into a little bit of the science behind tin construction. You see, most tins are built using a method called Delaunay triangulation. This approach chooses triangles so that no survey point falls inside the circumference of any triangle. The result is a set of triangles that avoids skinny, distorted shapes and instead maximizes the minimum angle. Why does this matter? Because well-shaped triangles create smoother, more stable surfaces. If you ever worked with a poorly triangulated mesh in software, you'll know the full frustration of jagged contours and unpredictable slope calculations. Delaunay triangulation minimizes those problems by keeping triangles as equilateral as possible given the data. So even here, the science of computational geometry underlies what looks like a simple drafting feature. Then we also have data compression. Another way to think of tin is a form of data compression. Consider this. The Earth's surface has effectively infinite detail. If you tried to model every pebble, blade of grass, and ripple in a ditch, you will never finish. Surveying is selective. We measure only what's necessary, and the tin reflects that selectivity. Instead of storing an elevation for every possible point, the tin stores just the surveyed points and the triangular connections between them. The triangles then interpolate the in-between areas. In this sense, a tin is a compressed version of the terrain, a faithful representation of the big features without drowning in unnecessary data. So, where do tins excel? Tins shine in scenarios where precision and local accuracy are essential. In things like road design, roads can cut across hills, valleys, and ditches. A tin can adapt to sharp grade changes and accurately represent the cut-fill conditions along an alignment. Drainage design. Water flows the path of steepest descent. Tins allow us to trace flow paths across irregular terrain, predicting where water will naturally accumulate. And we also have small site grading. For building pads, parking lots, and subdivision, details matter, and a tin can represent the subtle slopes that determine whether a site drains properly or floods. And of course, no model is perfect. Tins do have limitations. Discontinuities in tins assume that each triangle is a flat plane. If a hillside curves smoothly, the tin approximates it with a series of facets. The result is a piecewise surface that may look jagged compared to reality. There are also large area inefficiencies. For regional mapping, say an entire county, tins become computationally heavy. Thousands of points generate tens of thousands of triangles. For broad areas, a grid-based DEM might be more efficient and realistic to work with. There are also dependence on survey density. So a tin is only going to be as good as the data feeding it. If the survey crew misses a critical low point in a ditch, the tin won't invent it. It will interpolate smoothly across, potentially hiding important drainage issues. This last point is especially important. A tin is not reality. It's an interpretation of our real surface based on discrete measurements. The responsibility lies within the surveyor and drafter to ensure that the right points are captured both in the field and in our software. And it's worth noting that triangulation is not new. Ancient Greek mathematicians like Thales and Pythagoras were already thinking in terms of triangles when solving problems of land measurement. The very act of calculating distance by sighting across 2 points and forming a triangle is as old as surveying itself. What Civil 3D does through algorithms, surveyors once did by hand in chains and compasses and protractors. Using triangles to connect our known with our unknown. The modern tin is simply a digital extension of this oldest of surveying tricks. And for you, as future surveyors and maybe career draftsmen, the key takeaway is this. A tin is not just a software feature. It's a professional judgment tool. When you define break lines in a tin, you're telling the software where the terrain must not be smoothed over. That is an interpretive act, rooted in your personal understanding of how land and water behave. When you choose to densify points in an area of rapid slope change, you are changing the fidelity of the tin. And that is a decision with real design consequences. In other words, the tin is as much about your own professional judgment as it is about mathematics and representations of a surface. If you imagine the ground as a patchwork quilt, the tin is the stitching that holds the pieces together. Each triangle is simple, almost trivial on its own, but together, that network becomes a powerful representation of the land. It's flexible, it's detailed, and it's adaptable. That's why, for survey engineering, tins remain a gold standard of surface modeling when accuracy matters most. If the tin is like a flexible quilt stitched together from triangles, the digital elevation model is like graph paper draped over the earth. Instead of adapting to where survey points fall, a DEM imposes order. The land is divided into a uniform grid, and each cell in that grid is assigned a single elevation value. That might seem less elegant than a tin, but the digital elevation model has its own strengths, especially when we scale up from a site plan to a county, a watershed, or even an entire state. To understand the DEMs, let's start with the concept of gridding. Imagine you overlay a checkerboard onto a piece of land. Every square, no matter what lies within it, is given a single number, the average or measured elevation at its center. Now, if you zoom out, those numbers together begin to resemble the terrain. The valleys are represented by clusters of low numbers, the ridges by clusters of high ones. This is the principle behind a DEM. It's not trying to capture every nuance of territory, but to simplify it into a regular structure that computers and geospatial systems can handle efficiently. And a key concept in a DEM is its resolution, the size of each grid cell. High-resolution DEMs may have cells every meter or smaller, and this captures lots of detail. Small ditches, gullies, even road cuts may appear. Coarse DEMs may have cell sizes of over 30 meters, and they're going to smooth over many of those details, capturing only large-scale features like ridges, valleys, and floodplains. There's a clear trade-off here. Finer resolutions are going to mean more accuracy, but a lot more data and computational time. Coarser resolutions will sacrifice that detail, but allow massive areas to be modeled quickly and effectively. When surveyors or engineers talk about DEMs, one of the first questions asked will always be, what's our resolution? Because that number is going to determine what the DEM will actually be applicable for. And let's notice some philosophical differences here between DEMs and TINs. The tin is going to adapt to our data. It will reflect irregularities, it'll be dense where points are dense, and it'll be sparse where points are sparse. While a DEM is going to impose structure. No matter where the terrain changes, the grid doesn't bend. Everything must conform to its rigid spacing. This is a clear example of the difference between raster and vector data. This means a DEM sometimes misrepresents terrain in areas of sharp change. A steep ditch may fall entirely within a single cell, disappearing in that model, but at the same time, DEMs will excel at showing large continuous patterns, slopes across entire watersheds, and elevation gradients across entire mountain ranges. In short, TINs are about local accuracy, while DEMs provide a global perspective. So why do DEMs matter so much in survey engineering? That's because in survey engineering, many of the problems we face will be regional, statewide, not just site-specific. Take watershed modeling. DEMs are the foundation of hydrology studies. By analyzing these, we flow across thousands of grid cells, and engineers are able to trace exactly where water should drain, where basins are likely to form, and how floodplains will most likely develop. Through GIS integration, our geographic information systems are often going to rely on DEMs because the grids are computationally efficient. It's easier to overlay land cover, soil types, or zoning maps on a grid than it would be an irregular mesh of triangles. If you don't believe me, go open up ArcGIS Pro, try to pull in a full point cloud, for the coastal bend region, see how fast your software crashes, then try to pull in some raster data for it. That DEM is going to load fast, efficient, and provide a clear picture of that large area. And that brings us into planning at scale. Urban planners, environmental agencies, transportation departments, all will use DEMs to model entire cities and regions. For them, that fine detail of a single ditch is less important than the big picture of slopes and elevations across miles of land. And unlike TINs, which are usually built directly from our field survey data, DEMs often come from much larger scale data sets. Things like LiDAR. We can have airborne LiDAR campaigns generate point clouds across entire counties or states that will be converted within their own softwares into DEMs for use in others. In photogrammetry, we have aerial photos, which when processed with stereoscopic techniques, can yield elevation grids spanning entire nations. And government agencies, like the United States Geological Service, provides DEMs freely for so much of our country, and these are widely used in large-scale engineering and environmental projects. This means that DEMs are often a starting point for a project. They're providing context before detailed ground surveys are done. And a firm can begin with a 30-meter DEM just to get a base understanding of a watershed. Then they can go out and worry about collecting that precise GPS, total station, LiDAR, TLS data, and then they can build TINs for their specific site designs. And that gets into some of the strengths and weaknesses of DEMs. Efficiency, coverage, and compatibility are those strengths. So the grids are simple for computers to process. For algorithms for slope, aspect, and drainage are going to flow straightforward when the world is of matrices of numbers. It's not going to be difficult to do these. In fact, you're going to later on in this program learn how to do some of that by hand before you get into it with the software. Yes, there will be lots of math. Not in this course, but in your future courses in the program. There's coverage. DEMs can cover vast areas, like we said before, whole states and nations. Something that's just impractical for TINs, whether it be the issue of trying to compute it or just get it to load without our computers crashing. And then there's compatibility. Most GIS platforms natively handle raster grids, and that makes DEMs the lingua franca of spatial analysis, or it's the status quo, it's what we expect to see. Though we do have some very severe weaknesses of DEMs as well. It's that loss of detail that sometimes matters. Small features can disappear, especially at coarse resolutions. That narrow ditch that got removed from the data won't exist in our DEM, but it might end up being a critical feature for a specific project. And that's where the field crews come in. Then we also have the stair-step effect. Because our cells are uniform, the slopes can look blocky or steeped, especially when we have lower resolutions, as you can see in this graphic. And then there's the unimposed structure. Unlike TINs, our DEMs will not adapt to our data density. A single erroneous point can infect an entire grid cell. These weaknesses mean DEMs are rarely used for fine grading or construction design. And you wouldn't stake out building a pad from a DEM. But for planning and analysis at large scales, these are indispensable tools. Interestingly enough, DEMs do echo to some of the earliest ways humans represented land. Think about a medieval map that's been divided, that has divided estates into neat rectangular plots, regardless of how irregular the land may have actually been. The grid was a tool of governance and taxation more than just a reflection of our natural terrain. In a sense, DEMs are repeating that same logic. They're imposing order for the sake of clarity and efficiency. The land is irregular, but the grid makes it legible. Just as feudal lords wanted simple records for their holdings, modern GIS systems want orderly data structures. And let's not forget about DEMs in their role in grading. How do they properly connect to this? Now, it's mostly in the planning and feasibility stages of projects. Before moving dirt, engineers will likely use DEMs to ask broader questions, like how does this site sit within a larger watershed? Will grading here affect downstream flooding? And where are the natural ridges and valleys at a more regional scale? Once the design moves into detail, DEMs are going to give way to TINs. But at the conceptual stage, at the planning stage, DEMs provide the canvas on which our larger projects will eventually be drawn. So if the TIN is that close-up, high-resolution photograph of terrain, the DEM is the satellite image. It's less sharp, but it's covering the whole landscape at once. Both are valuable, but for different reasons. As professionals, your role is to know when to use each and to recognize the trade-offs inherent in each model. So let's move into contours. If TINs are the mathematician's tool and DEMs are the planner's grid, then contours are the communicator's language. Contours are lines that connect points of equal elevation, creating a picture of the land that is both analytical and intuitive. Long before computers could interpolate surfaces, engineers, cartographers, and surveyors relied on contour maps to see the shape of the Earth. And even today, in an age of 3D modeling and LiDAR, contours remain the most common and accessible way of representing terrain. A contour is, at its simplest, a slice of the Earth at a given elevation. Imagine you're standing at the edge of a hill while water rises like a flood. At each foot of rise, the waterline traces a closed curve around the hill. Those curves are contours. They reveal the land's shape by showing where elevation is constant. This ideal of slicing the Earth into level curves is fundamental in the mathematics. In calculus, we call them isopleths. In geography, we see them not only as elevation contours, but as isotherms, lines of equal temperature, or isobars, lines of equal pressure. Contours are a universal language of surfaces. So why do contours work so well? Well, they're powerful and they work well because they compress three-dimensional terrain into 2 dimensions without losing meaning. Their spacing tells slope. Close contours mean steep slopes. Wide contours mean gentle slopes. Shapes tell form. V-shaped contours point upstream in valleys. Concentric circles indicate hills or depressions. And continuity tells flow. Smooth, evenly spaced contours suggest gradual, natural terrain. Jagged or irregular contours will likely reveal man-made cuts or even errors. In other words, contours allow the human eye to instantly grasp the lay of the land. That's why they've endured for centuries, even as digital modeling has advanced. For engineers and surveyors, contours aren't just pictures, they're decision tools. Taking drainage, for example. By reading contours, you can predict where water will flow, where it will pond, and where to place culverts or ditches to relieve areas of flooding. In design feasibility, a site with evenly spaced contours will be easy to grade. A site with chaotic, steep contours may become impractical, too costly to even consider developing. And then, even with cut and fill analysis, proposed grading is often shown as new contour lines overlaid on existing ones, allowing engineers to visualize exactly how much earth will be moved. That's why Civil 3D and other CAD systems generate contours dynamically from surfaces. They turn raw data into the language that engineers, contractors, and even clients can read. And one of the subtleties of contour mapping is the choice of contour interval, the vertical spacing between lines. A 2-foot interval might be chosen for a small, detailed site, like a subdivision, while a 10-foot interval might be used for large topographic maps, where fine detail would clutter the drawing. This choice is not arbitrary. It balances clarity with accuracy. Too fine of an interval and the map becomes unreadable spaghetti. Too coarse and important features begin to disappear. Selecting the proper interval for your project is an act of judgment, reflecting both the scale of the map and the purpose of the survey. Conceptually, contours sit between 10s and DEMs. From a 10, contours are generated by interpolating across the triangles. Each triangle is sliced at regular elevations, and the slices are then connected into smooth lines. Contours from a DEM are generated by interpolating across grid cells, producing lines that approximate equal elevations. In both cases, the contour is not a new dataset. It is a visualization derived from a surface. That's an important distinction. The surface holds the data. The contour is simply how we see it. And contours have revolutionized mapping when they were first introduced in the 18th century. Before that, maps relied on pictorial symbols, little sketches of hills, shading, and hatching short parallel lines indicating slope. And these were artistic, but they were not quantitative. Contours changed everything. Suddenly, maps could not only show a hill, but also tell you its height, its slope, and the relative difficulty of traversing it. Military strategists, civil engineers, and planners quickly embraced the method of making contour maps. In fact, one of the earliest wide uses of contours was for canal construction in Europe, where engineers needed precise slope information to design locks and channels. Later, the U.S. Geological Survey adopted contour mapping as the backbone of its topographic series, which remains some of the most detailed public maps available today. So when you look at a contour map, you are not just seeing a visualization, but a centuries-old tradition of scientific and geospatial communication. In the context of grading, contours also become contours also become especially powerful. Think of a proposed subdivision plan. The engineer drafts new contours, smooth, evenly spaced lines, overlaying the jagged, irregular contours of our existing ground. The comparison reveals the earthwork required, where the site must be cut down, where the fill must be placed, and how stormwater will eventually flow across a finished site. Contractors then build directly from those contour-based plans, using them to set grades and elevations in the field. A contour map in that sense is not just a drawing, it's a construction instruction, telling machines how to reshape the land. And finally, let's not forget that contours are one of the few surface representations that non-specialists can understand at a glance. A developer, a city council member, even a homeowner may not know what a TIN or a DEM is, but show them a contour map and they will likely be able to intuitively see where land is high, where it is low, and how steep it is. That makes contours one of the most democratic of surface tools, a bridge between the technical world of survey data and the lived experiences of people. Contours remind us that surveying and engineers are not only technical, but they're also communicative. The lines on the page are not just geometry. They are stories of ridges, valleys, slopes, and plans. They are how we share our knowledge of the land with others. And as we'll see next, once we have surfaces and contours, the next step is to begin reshaping them. That's where grading groups comes in, the tools and theories that let us move from this is the land as it is to this is the land as we need it to become. So far in this lecture, we focused on surfaces as representations. TINs, DEMs, and contours all describe the land as it exists. But in survey engineering and civil design, the story doesn't stop at visualization of the existing world. At some point, we must transform these representations, cut down a slope for a roadway, raise a pad for a building, carve a basin for stormwater management. That process of deliberate transformation is grading. And just as surfaces provide a mathematical model of the land, grading provides a mathematical model of its reshaping. In modern software like Civil 3D, grading is organized into grading groups, collections of related grading objects, slopes, pads, daylight lines, and feature lines. That together define a proposed modification to the real world. But before we get too technical, let's unpack some of the concepts behind grading itself. At its core, grading is about balancing geometry, physics, and practicality. With geometry, the new surface must tie into the existing ground at specific slopes. A driveway must slope towards the street at 2%. A building pad must be level. A ditch must maintain a minimum fall. With physics, water will always flow downhill, and soil has limits of stability. Too steep a slope may erode or collapse. Too flat a pad, and ponding water may occur. Practicality. Moving earth is expensive. Every cubic yard of cut or fill costs money in hauling, compaction, and disposal. A good grading design will minimize unnecessary movement of soil, particularly from your site. So grading is not arbitrary drawing. It's not an optimization, or it is an optimization problem. One that balances safety, cost, drainage, and constructability. In Civil 3D, a grading group is essentially a container that will hold related grading objects as it ties them back to a parent surface. Conceptually, you can think of it as the mini surface built for a particular purpose. A building lot, a roadway section, a detention pond. Why group them? Because grading rarely happens in isolation. A pad isn't just a rectangle on a hill. It has slopes that daylight into existing ground. It has drainage paths that must tie into ditches. And it may sit next to other paths that must align at shared property lines. By grouping these together, we ensure consistency and allow the software and ourselves to calculate volumes, adjust slopes, and rebuild surfaces as changes ripple throughout our designs. So let's talk a little bit about daylight lines and slopes. One of the most fundamental ideas in grading is the daylight line. That's the line where proposed grading meets existing ground. Imagine cutting a hillside for a road. That slope extends outward until it meets the natural slope. That edge is the daylight line. Similarly, when you place fill to raise a pad, the slope extends until it ties back to the original surface. In grading groups, daylight lines are crucial because they define the transition between human intention and natural terrain. They are literally where the design meets reality. And then we have pads, slopes, and transitions. Within our grading group, these different objects work together. Pads are flat or nearly flat surfaces for buildings, parking lots, and roads. Slopes are graded connections from our pads to our existing terrain, defined by things like ratios 3:1 or 4:1, horizontal to vertical. Transitions are our complex areas where multiple slopes intersect, requiring careful control to avoid an awkward geometry or drainage problem that causes further issues in our project down the line. Each of these objects is mathematically simple, but when combined together, they create a new surface that must behave predictably under both human use and natural forces. Then we have volumes, or cuts and fills. And one of the main reasons that grading groups exist is to calculate these earthwork volumes. Our cuts are talking about our soil that needs to be removed from an area. Our fill is the soil that needs to be added. Balancing our cut and fill within a single site is both an economic and environmental goal. Too much excess cut and you must haul soil off-site. It's costly, it's disruptive. If you have too much fill, you're having to bring in too much soil. And that is also going to be costly and sometimes environmentally unstable. Good grading design strives for a balanced site, where cut roughly equals fill. Your grading groups allow engineers to calculate this balance with precision, and minimizing that cut-fill ratio is what we're looking for. But grading is not just about cut-fill, and it's not just science. There's also a bit of an art to it. A site that looks natural after grading is often going to be more stable. It's more attractive to clients, and it's more acceptable to regulators. A site that completely ignores natural terrain, carving rigid artificial slopes, may work on paper, but it fails in reality, with erosion, drainage complaints, and plenty of community opposition. This is why experienced engineers and surveyors often talk about reading the land. They use contours, TINs, and DEMs not just for calculation, but as guides to design grading that works within the terrain instead of against it. And for you as students, grading groups are valuable not only because they're a feature in Civil 3D, but because they embody a way of thinking. Design is systemic. You cannot design a pad without considering its slopes. You cannot design slopes without considering their daylight lines. And you cannot design daylight lines without considering the overall surface. Grading groups force you to think holistically, ensuring that your modifications connect back to that bigger picture. And it's also worth noting that grading is one of the areas where professional responsibility is most viable. Engineers assign and seal grading plans, certifying that slopes are stable, that drainage is adequate, and that our cut-fill balances are reasonable. Surveyors often provide the existing surfaces and may also stake out grading lines in the field. And that our drafters play that key role in modeling the surface, ensuring that the digital grading reflects both the engineer's intent and the site's constraints. Errors in grading design can have immediate costly consequences. We're talking flooded basements, unstable slopes, over budget earthwork. That's why grading groups are not just a drafting exercise, but a professional responsibility. Because our grading groups represent that transition from what is to what will be. They're allowing us to model, analyze, and optimize the transformation of land in a way that respects its geometry, physics, economics, and aesthetics. In that sense, grading is the ultimate expression of survey engineering. It's the science of measurement and surfaces combined with the art of design and construction. Today, we've taken a journey into one of our most technical, but also most conceptual aspects of survey engineering: surfaces and grading. We began with this idea of a surface itself, that mathematical representation of the Earth's terrain. We've built to translate scattered measurements into continuous models. From there, we've explored three primary ways surfaces are represented: our tin surfaces, our DEM surfaces, and our contours. And then we turned to grading groups, the tools and concepts that transform those representations into actionable designs, balancing geometry, physics, and practicality. If there's a common thread connecting all of this, it's the theme of translation. Our survey crews collect discrete points. The surface then translates those points into a continuous model. The drafter translates that surface into contours that others can read, and the engineer will translate those contours into grading plans that reshape the land. At every step, professionals are making interpretive choices: which points to measure, which break lines to enforce, which contour interval to use, and which slope ratio to design. None of these are automatic. Each involves judgment, experience, and responsibility. Surfaces and grading remind us that surveying is not just measurement, and drafting is not just drawing. Together, they are acts of meaning, turning irregular, messy reality into models and plans that society can act upon. One of the goals of this course and this lecture is to emphasize the science between what might otherwise seem like drafting commands. Today, we saw that tins are built on our principles of computational geometry. We saw that DEMs are rooted in raster mathematics and resolution analyses. We saw that contours reflect concepts of isoplests and level curves from calculus and geography. And we saw that grading integrates physics, the water flow, soil stability, with an optimization of problems in geometry and economics. When you sit down at your computer and open Civil 3D, and you start clicking through your toolbars during our labs, you are applying centuries of mathematical thought in engineering science, probably without realizing it. Having an awareness of this is what separates the technician from the professional. Because don't forget, you are not here to become a CAD tech. You are here to become a surveyor, to become a GIS professional, to become a geospatial engineer. And that brings us to that critical point of surfaces and grading carrying real weight. Our mismodeled surfaces can potentially hide drainage problems. Careless contour intervals can mislead contractors. And grading plans that ignore cut and fill balances can completely bankrupt a project. For licensed engineer and surveyors, errors in these areas can result in lawsuits, liability, and real-world consequences. For drafters, it means your work is not simply clerical. You are a participant in professional judgment. These drawings you produce are not just technical artifacts. They are legal, financial, and social instruments. Communities are built or flooded on the accuracies of the surfaces and gratings that you will produce. So when we step back, surfaces and gratings sit at that intersection of two fundamental human impulses: to measure and shape. Measuring is what we do when we create a surface, turning the raw, irregular land into something legible. And shaping is what we do when we grade. We're transforming that land into something useful, livable, and sustainable. This pairing, measurement and transformation, is as old as civilization. The Egyptians measured and shaped floodplains for farming. The Romans measured and shaped hills for aqueducts and roads. Today, we measure and shape subdivisions, highways, stormwater basins, everything around you. The technology changes, but the principles remain the same. So, looking forward, in lab this week, you'll see the technical side of this lecture come alive. You'll be defining surfaces, examining properties, creating tins, exploring break lines, and even calculating some cut fill volumes. But remember, the lab is just showing you the how. This lecture is the why. If you keep that distinction in mind, theory and lecture, application and lab, you'll build not only technical skills, but also professional wisdom. So as we close, I want you to carry away 3 key ideas. Surfaces are not just digital models. They are translations of reality into meaning. Contours endure because they are the most intuitive language of terrain, accessible to both experts and the public. And grading is where measurement becomes transformation, the point at which surveying and engineering directly shape the world we live in. By mastering these concepts, you are not just learning software. You are learning to see land the way professionals do, not as raw ground, but as a system of surfaces to be understood, communicated, and reshaped responsibly. That's the essence of survey engineering, and that's the responsibility you're stepping into.